Welcome. In this video, we're going to talk about types of reactions. When you look at chemical reactions, there are so many of them that if you try to memorize each reaction individually, it would be absolutely overwhelming. So we're looking for patterns, for ways to recognize how the reactants and the products are changing and how they're related to one another. There are several different ways to organize reactions, and we're going to look at several of those throughout the year. But this way I'm going to talk about today basically puts reactions into one of 5 categories, and it's what you typically learn in first year chemistry. So the first type of reaction we're going to talk about is called a synthesis or a combination reaction. And in a synthesis or a combination reaction, you have 2 different reactants. And those are going to combine to form a single product. One example of a synthesis or combination reaction would be the reaction between solid iron and oxygen gas to form solid iron 3 oxide. And you'll see right over here down below I have it written both as a chemical equation and as a particle visualization. And it's going to be really important as the year goes on that you're comfortable in working in both formats. So the second type of reaction is a decomposition reaction, and it looks very much like the opposite of a synthesis or combination reaction. I have a single reactant, and I'm going to form 2 or more products. So for example, I can take calcium carbonate, which is a solid, and if I heat it, and that's what this little triangle over the arrow means. If I heat it up, it will decompose to form calcium oxide and carbon dioxide gas. The third type of reaction is a combustion reaction, and we're really talking about the combustion of a hydrocarbon. And so as you look at the name, a hydrocarbon has at its backbone hydrogen and carbon. There can be other elements in a hydrocarbon, things like nitrogen, oxygen, the halogens, but it will always contain carbon and hydrogen. And that hydrocarbon is going to be able to react with oxygen gas, and it forms carbon dioxide and water. So for example, if I have C3H8, that's propane, like you would have in your gas grill, it'll react with oxygen gas, and it'll form carbon dioxide and water. In a single replacement reaction, we have an element that's by itself as well as a compound. And then when the reaction occurs, on the other side you get a different element and a different compound. One example of this is the reaction between aqueous chlorine and aqueous potassium iodide. So the chlorine is the element that's by itself, and then the potassium iodide is the compound. And when these come into contact, they react, and you end up with potassium chloride and iodine. So now you have a different element by itself and a different compound. Lastly, we have double replacement reactions. In double replacement reactions, you have 2 different compounds as your reactants, and you get 2 new compounds as your products. These are typically ionic compounds, and the anion and the cations trade partners. So if we look at the example, we have potassium sulfide, where the potassium is 1 cation, and the nickel nitrate, the nickel is the second cation, and then the anions are the sulfur and the nitrate. And those are going to trade. So the nickel was combined with the nitrate. In the product side, I have the nickel combined with the sulfur. And the potassium was combined with the sulfur, but now it's combined with the nitrate. Do note that when you make these products, you're making 2 new ionic compounds. You need to make sure that the charges are canceling out. So the charges won't change from left side to right side when you go to write these reactions. On the left-hand side, the nickel had a +2 charge because it was combined with 2 nitrates, and so it has a +2 charge on the right-hand side. Nitrate's always -1, so nitrate's -1. Potassium's always +1, those alkali metals. And then sulfur is going to be a -2. And so you'll see that the subscripts on the right-hand side of this equation are different than the subscripts on the left-hand side of this equation because the charges of what's combined are now already matched up. So +2, -2, +1, -1. So we didn't need the subscripts that we needed over here in order to have these compounds have charge neutrality.